Welcome back. We are now moving on to chapter 9. This is a pretty hot topic, I think you could say, in the history of cognitive psychology. All of this research on judgment and decision making, um, gives us one of our few Nobel laureates in psychology. To be fair, Daniel Kahneman and his collaborator Amos Tversky had received their Nobel Prizes in economics, but they are working in a field that we could call behavioral economics, maybe cognitive economics if you wanted to. I've never heard that word used, but it kind of makes sense to me. Um, and so you may have seen Kahneman's book here, Thinking Fast and Slow. So if you haven't, check it out. It's probably worth a read. Um, so we're going to start here, and we're going to then get into some of the work that he and Amos Tversky are most famous for, and a few of their other collaborators too. So we're kind of revisiting cognitive control for a minute here. As you recall, in that chapter, we talked about automatic and controlled processes. And so, just as a reminder, an automatic process is one that happens very quickly, nearly involuntarily, whereas a controlled process is slower and deliberate. And importantly, when we talked about these things, we talked about them using up some limited amount of so-called cognitive resources. Um, so that we want to keep that in the back of our mind when we think about what Kahneman refers to as system one and system two processes here. So system one, here we're defining reasoning really. They're not just general cognitive processes, right? These are types of reasoning, but they do maybe align a little to automatic and controlled. System one is fast, right? So you can compare that to automatic processes. And what we would say is that there's a little less cognitive control, a little bit less effortful processing involved here. And so we might sometimes say that these kinds of judgments or reasoning processes that we're engaged in that happen so quickly, we could compare them to situations where we might just be going with intuition, right? Like I'm presented with a problem, you ask me a question, and instead of carefully thinking about it, I'm just going to give you my gut feeling, like this is what I think is the right answer. Here you go, right? So I'm going to just blurt something out. And so we might ask the question, how good are we at doing these kinds of things, right? Can we really just go with our gut and intuit answers to questions, and or is this going to lead us to making mistakes and to being wrong a lot? And I think what we're going to see as we go into this is the answer can be a little bit of both, right? Um, so we can be good at this, but it's not going to give us perfection necessarily. Now, system two, on the other hand, is the stuff that's a little bit more slow and careful and deliberate. So it might seem natural for us to think that that means that we're much more likely to, uh, carefully reason out to a correct answer. But at the same time, there's also the possibility that when it comes to trying to be careful and to bring in all of the relevant information that we need to deliberate on a good, solid, rational answer to a difficult problem, that maybe we are not necessarily really good at that either. And so you see, I have these question marks on here. The system one seems like it might be more likely to be irrational, but is that necessarily true? And system two seems like it might be more likely to be rational, but again, is that necessarily true? Let's get into the details, shall we? Let's talk about rationality for a second. So we need to start with a point here, perhaps, which is as cognitive psychologists, as experimental psychologists, our goal ought to be what I have right here on the top of this slide, that we want to understand human behavior. And if we are a cognitive psychologist studying judgment and decision making, then we want to understand human judgment. And sometimes we phrase it this way, judgment in the face of uncertainty, because that's sort of an implied component here. Maybe I need to spell that out. When I'm making a decision, I usually am trying to think about what's the best choice to make. but I don't know for sure what the best choice is necessarily, not until later, perhaps, right? And it could be something as mundane as um, you're with a friend or a partner and you're saying, "Hey, we're going to go out to eat tonight. Where do you want to go?" I don't know, right? And you have these debates, but now you're faced with making a judgment, right? Of all of the choices that we can think of, which one is the right one? Which one is the best one? And there's uncertainty involved because you could think that, okay, we've been to such and such restaurant several times, and every time we go, we tend to do okay there. We like the food, price is okay, you get good service, you don't have to wait too long to get a seat, and all this kind of stuff. And so you're thinking, that seems like the best choice, but there's no guarantee because you might go there and they're having an off night and the service is bad and the food is bad and so forth. So it turns out your judgment was wrong, right? So our goal, though, is when people are faced with having to make these kinds of decisions, and they're faced with some level of uncertainty, what are the ways in which people reach these decisions, right? That's our goal as a scientist, is to describe and understand the ways in which this happens. But that's not necessarily, the reason I'm bringing this up is that that's not necessarily how research on judgment and decision making has always progressed. If I had any kind of nit to pick about this research from Kahneman and Tversky and others, it's that they may have taken what we might consider to be more of what's called a normative approach, whereas what I have just described is what we would call a descriptive approach, right? To take a descriptive approach is to say, how do humans make decisions? I don't know. Let's go study them and find out. And we're going to observe and describe human behavior and do some research and then come up with some explanations and principles and theories and models that can explain human reasoning and decision making and judgment. But a normative or a prescriptive approach works a little bit differently. It starts not by asking the question, how do people do this? But rather it starts by asking the question, what's the best way to do this? And that means defining rationality. If we assume that being perfectly rational is to make one an optimal decision maker. And so we're going to define optimality as perfect rationality. And then we're going to have this in the back of our mind to say, this is the right way, this is the optimal way to solve this problem. So let's give this problem to humans and see what happens. And oh, look, they didn't do it this way that we said. So therefore, what does this prove? It proves that humans are irrational. This might be true, but maybe it rubs me the wrong way because it seems to have some sort of inherent judgment associated with it that we're basically saying this is the right way to do it, and then when we ask people to do it, we see that they're doing it wrong, and just look how irrational and stupid people can be, and that's not science really, right? But let's just take a look though at the at kind of the issues here. So one way to approach optimality is to think about decision-making formulas, right? So a formula is synonymous with the idea of an algorithm. So here we have an algorithm, right? Or the definition. We have a couple examples of algorithms here. An algorithm is basically a formula that solves a specific problem. That's kind of critical, by the way, the emphasis there on a specific problem. So let's take the example of long division that I have here on the screen. You learned this in, I don't know, I think I learned long division in third grade. Is that still done? And so there's a formula, right? You learn that if I tell you that you need to divide 6,365 by 20, you know the steps to perform. The first thing you do is you write the 6365 on a piece of paper. You write that little half a rectangle thing. I don't know if that's called something there. Probably does have a name over it. And then you write the little 20 to the left, and then you start dividing. You try to divide 20 into 6, and then that doesn't work, so you put a 0 up there. So then you divide 20 into 63, and you think, oh, I can do that 3 times. So 3 times 20 is 60. You write that below the 63. You subtract that out, and you get the 3. You carry the 6 down. So now you ask how many times does 20 go into 36? That's 1 time. So 20 times 1 is 20. Subtract it out, and on you go. You know how this works, right? And so then you can calculate an answer. And so that's a formula, right? And you can learn how this formula works, and then you can apply this formula, and that's an algorithm as well, right? And so that makes you once you learn this technique, you can be an optimal reasoner when it comes to long division problems. But what's critical about this, of course, is that this formula, which is quite useful for long division, is only useful for long division, right? So that means that being good at this is doesn't necessarily mean that you're always good at solving other kinds of problems. It means you're good at solving long division problems. So that's not necessarily um, um, going to necessarily help you in all domains of life, right? But what's also critical about this here is that while we can learn how to do long division, even as relatively young children, say in third grade, um, it is still something that is a little bit difficult, right? So if you recall, I certainly recall that when I first learned long division, I didn't perfect it, right? I made a lot of mistakes and I struggled with it a little bit. And so that means that we're, our brains are not quite the same as, let's say, a calculator. Because what is a calculator other than a set of circuits that takes the algorithm of long division and has hard coded that into the circuitry so that now this circuit board or computer chip can execute this algorithm over and over and over again. And what happens here is that it does it very, very quickly. And importantly, it never makes mistakes, right? Assuming you don't make a mistake typing your numbers into the keyboard on your calculator, the calculator, it doesn't fail, right? It always will execute the algorithm perfectly and exactly and quickly every single time. What we see about humans is that the exact opposite is true, right? It is slow and effortful, and we are prone to making errors. We might make a mistake. So do we use algorithms? Yes. Are we good at using algorithms? And the answer might be no. My other example is GPS instructions, right? And the idea is that if I want to figure out how do I drive from point A to point B in a city, say Orlando, then I can use an algorithm for that, right? And I don't necessarily know off the top of my head how to do that. I could probably get out a map and start calculating distances, but certainly it's nice to have a computerized tool to do that for me. And that's what it does, right? So the GPS software has access to a map system. It knows where you are. It knows where your destination is, and it can calculate the miles that it would be required to travel if you take this route versus another. So it can calculate the shortest distance route. If you give the software a little more information, like the speed limits on these roads, it might even be able to separately calculate the fastest route, which might be different than the shortest route. If you give it more information, like a lot of phone apps will have extra data coming from other users about road conditions like closures and traffic congestion and so forth. And so it can factor that in. So again, it's just going to factor in information. But there's always going to be something that might still be unpredictable here. So what's kind of critical about this kind of algorithm is that it works, but it works within a very limited range of circumstances, and there can always be something that's unpredictable and cannot be accounted for by this fixed formula, right? So here we see that algorithms can be used as one way of defining optimality, but one of the things that we're sacrificing with optimality is we're sacrificing flexibility for unpredictable and novel situations, and we're also sacrificing just general ability to solve different kinds of problems, right? Algorithms are almost necessarily defined as being very highly specific, right, for a specific kind of problem to be solved. So what's the alternative to an algorithm? And well, that's a heuristic, right? It's defined here as a rule of thumb. And we could compare, the algorithms to that kind of system two thinking because they are effortful. So a heuristic could be more like that intuitive system one kind of thinking, right? It's much less effortful. I don't have to think so hard, right? So in using the long division example, I could say what's 147 divided by 7. And if I wanted to know the answer, I could sit down and do the algorithm and calculate it out. But if I don't happen to have a pencil and paper ready or a calculator ready, and I don't necessarily care about being perfectly accurate, then I could simply just say, I guess it's around 20, right? 20 point something. And and uh and that's enough, right? So it's not a perfect answer, but it is an approximate answer, but it was an approximate answer that did not require very much effort whatsoever, and I could do it very quickly. But obviously then it's prone to a little bit bias in the sense of it's not an exact and accurate answer. The same goes for navigation, by the way, because here the idea is that if I've lived in Orlando for a very long time and I need to go from, say, the UCF main campus down to the UCF downtown campus, there's a few different choices that I could make for that. And I could certainly let GPS tell me that, but I might also just use my intuition. And I say, well, it's what is it right now? It is nearly 1 p.m. in the afternoon. So I'm thinking, okay, 1 p.m. That probably means that the 408 is pretty clear. So I'll take that because that'll be fast. But if it's closer to some other time of day where I might think, yeah, that's going to be a busy road, I'm just going to take some different route down there, right? Surface streets. Then that's using my judgment, right? So that's a heuristic. I could be wrong, right? Who knows, right? But the idea is that that's just my heuristic that saves me a lot of effort. It's a lot quicker and easier than having to map anything out. And it could be correct most of the time, especially if I'm drawing on, say, a long time of experience living and driving around in whatever city I might live in, right? But there's something else that we really need to talk about here. Doing long division and solving navigation problems are what we can call well-defined problems. And by a well-defined problem, what I mean is that we have a problem that has a clear-cut solution here, right? Which is, I want to know the exact answer to this math problem. There is one right answer. Or for a navigation problem, I want to get to this destination in the shortest distance. There is one right answer for that. And or if it's even in the shortest amount of time, there may also be exactly one right answer to that. And I have enough, and if I have enough data, then I can calculate the exact right answer to that, right? So we have a very clear, well-defined one answer that we're trying to get to, and we will know it's the right answer when we get to it. But on the other hand, there are other kinds of problems, ill-defined problems. And what we need to think about here is, can we have an algorithm for them? And I don't think so, right? So I have a list here of ill-defined problems, right? You have to pick a major. So let's try to think about an algorithm for selecting a major. So one of the things that I could do is I could think about the kinds of jobs that I might get if I were to pick a certain major. And then I could think about the things like, what's the job market like? What is the salary? Where would I live? How demanding would the job? Do I think I'd be successful in the job? Would it be something I think I'm competent to do, that I would even enjoy doing it? And I could try, and maybe I also need to think about the school. Like, I think would be a good job, but I also have to think about how is this department at this university? Is it a good department with good professors and lots of good opportunities, or is it got a bad reputation, right? Those are all these different things we might have to think about. So we could try to turn this into an algorithm if I could find some way to quantify and maybe even put an index by every single one of these variables, and then put them all together into some kind of an equation, like a linear equation, and just kind of put it all together, and I could generate predictions, right? This is like a multiple regression in a way. And I could calculate expected values and expected outcome values for all of these different majors. And I could just pick the one that has the best expected value. So that would be a way of doing it, right? Now, the first question I could ask is it possible to do this? Can we really kind of index all of these many different variables accurately and come up with a reliable calculation of expected value for every single major choice that we have at our disposal? Probably not. So that's our first strike against this whole approach is that um, it's not clear that even though we can conceive of such an algorithm, whether we could really create it is another question entirely. But let's assume that we could do that if we just pretend that we can create this algorithm. Is this algorithm guaranteed to work? And so that means that let's say that I do it. Let's say that I find the major that has the highest expected value for me, and I pick that major. And then what happens? What does that mean that I'm going to get A's all through this my college experience and succeed and graduate and get a job and be happy and make a lot of money and do all these things? No, none of that is guaranteed just because that major happened to have the highest expected value calculation based on my algorithm. So that makes this an ill-defined problem, right? Even the best heuristic that we can think of, or sorry, the best algorithm that we can think of does not give us a guarantee of success here. So it's quite likely that we wouldn't even bother with this, right? Why bother with that? I'll do all of that work if I'm still going to think, I'd still rather pick this other thing instead, right? So, the algorithm says to do this, but I'm just going to go with something else because it feels right. And does this, it feels right judgment, which again, it's a heuristic, it's that intuition, it's that gut feeling. Does that guarantee a correct answer? No. But is it a lot easier to do it than the algorithm? And yeah, definitely, right? So now the next question, though, is if both of these approaches are not guaranteed of delivering a perfectly definitively right answer, is one maybe better than the other, right? So maybe they're both imperfect, but maybe I'll have a slightly higher odds of better outcome if I choose the algorithm instead of the heuristic. We don't know that, right? There's not really even a good way of calculating and comparing this. And so the idea is that, generally speaking, and of course, this is related to what I was trying to get at before. Algorithms are for very specific and well-defined problems, and these heuristics work much better for these other kinds of situations here. And in fact, what's also critical here is I had a note about our brains not being computers. Most of the decisions and the judgments that we have to make in our regular everyday lives are actually ill-defined kinds of problems. Computers, at least in the era of pre-AI, were never good at solving ill-defined problems. And it might still be the case that AI is not necessarily good at solving ill-defined problems. But old-fashioned computing, at least, was certainly not well suited at all for this. But what is the human brain good at if it's not a computer and it's not good at executing algorithms? Well, it's good at ill-defined problems, right? Now, that doesn't mean that we always win. That doesn't mean that we are always in the best possible situation in our lives because we're solving ill-defined problems with optimality. But what it means is that we can handle ill-defined problems, right? So when it comes to all of these difficult choices we have to make in life, all this list of things that I have here, we can work within that, right? And it's not always perfect, but that's what cognition is like for humans, right? We have the flexibility to apply this heuristic, intuitive, gut level kind of judgment to all of these very different, and there's the heuristic bit, right? Is that it's not domain specific, right? It's not just about solving this kind of problem. It's a kind of way of thinking about problem solving that works in all of the various types of ill-defined situations. So my little nitpick that I mentioned before that there's this tendency to point out that people are irrational because they don't use algorithms and they rely on heuristics. But what makes heuristics bad, right? Heuristics are actually good. They are very, very useful at solving ill-defined problems, and algorithms are not. So, given that our lives are typically shaped by these ill-defined problems, this is actually quite unex this is quite expected, right? This is a expected finding. But a lot of the judgment researchers have treated it as a surprise, like, oh my gosh, no, right? So I'll try to avoid continuing on, kind of beating on that particular point. Um, but we do need to talk about the idea of the specific types of biases that have been described in this research that I'm complaining about here. All right, so let's talk about the base rate fallacy here. So base rates refers to statistical base rates, the basic probability of something happening. So let's look at this first example. This is an example of something known as the representativeness bias, and this is an excerpt from actual research. So people are presented with a profile of a fictional person named Steve, and we see it here. Steve is very shy and withdrawn, invariably helpful, but with little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. Now we are asked, do I think Steve is more likely to be a librarian or a farmer? So this is called the representativeness heuristic because what's going on here is that people are going to answer that they believe Steve is more likely to be a librarian because this little profile description of Steve seems to match what people think of as the stereotype of a librarian versus the stereotype of a farmer. So that means that Steve's behavior here is representative of librarians more so than being representative of farmers. Now, is this wrong? It could be wrong. And one reason why it could be wrong is we simply just don't know if Steve really one or the other, and is this information diagnostic? And part of the point is that maybe it's not diagnostic, right? And maybe what's going on here is that we need to think about something else, which is that if Steve is just some random person that we've been given some information about, well, out of all of the many people in the world, there are many more farmers than there are librarians. Being a librarian is a pretty niche kind of job, I guess. So what we would say here is the statistical base rate of Steve being a farmer is much higher than it is as a librarian. But apparently people don't use this information, right? People don't think, oh, well, the likelihood, so I'm literally asked, is Steve more likely to be a librarian or a farmer? And given how few librarians there are compared to how many farmers there are, our answer ought to be that he's more likely to be a farmer. But of course, the answer is, or what we see in the research is that people say he's more likely to be a librarian because he represents some stereotype that we have, right? Now, one question we could ask if we wanted to push back a little bit on the conclusion here that people are being irrational by exhibiting this representativeness heuristic is we could ask, how do we even know that people know this, right? I just said that there are many more farmers than there are librarians, but is that common knowledge? And some have argued that it ought to be common knowledge because if you think about it, you think, yeah, there's a lot of farmland and there's a lot of food that has to be grown to feed everyone on the planet. So there must be a lot of farmers, but how many libraries are there, right? Not many, and therefore there's not very many librarians. So if you think about it for just a few minutes, you would probably and correctly determine that, yeah, there's probably more farmers in the world than there are librarians. But even if we could kind of, reason that out, we don't go to that effort to even think about this, right? We don't even bother to think about the actual statistical base rate. And maybe that's their larger point here is we could take that base rate information into account, but we don't even try, right? Instead, we just go with the information as given and he matches this representation or stereotype about librarians, and that shapes our answer. Here's a related one that exhibits a similar kind of base rate error. But one of the things we could do here is that if people are not necessarily thinking about the base rates of librarians and farmers when presented with this little profile of Steve, what if we make it a little bit more obvious? we're gonna give you those base rates. We're gonna make them front and center as part of this question. So we're now going to say that we're going to give you a profile of a person named Jack. But before we tell you about Jack, we're going to tell you that this profile of Jack has come from a panel of psychologists who interviewed and administered personality tests to 30 engineers and 70 lawyers. All right, so we have a sample of 100 people here, and Jack is one of these 100 people. And we are told right here at the beginning that out of that 100, 30 of them are engineers and 70 are lawyers, and successful at each. I guess that successful line is important because we want to think that every of these one of these 30 engineers is a successful engineer and therefore is a representative of their profession, right? And same for our 70 lawyers. So now we are going to give our subject this profile of Jack, and then we're going to ask them to rate the likelihood we think that Jack is an engineer on a scale from 0 to 100%. And so you can read the profile for Jack here. I won't read it aloud. And then again, we're going to ask people, what is the probability that Jack is one of the 30 engineers in the sample of 100, right? Again, we're making the statistical information really salient here to ensure that people are going to try to think about it. And they still say some number that's higher than 30, right? They're going to give some bigger numbers. It may not be 100%, maybe it is, but maybe they just go 90% or 80% or something like that. And so again, we're going to say, look, in that librarian versus farmer thing, they don't think about the base rate, but maybe it's because that was kind of far from their mind, and they didn't have access to that information. But here we're making all of that information, salient and plain as day, and they're still not using it, right? They're still not taking it into account. So again, they're misusing this kind of statistical base rate information that, in fact, is somewhat relevant to the question of the probability that Jack is a engineer from this sample. Okay, but there's another thing that we might need to think about here. Yes, it could be true that people are very bad at using statistical base rate information. But what's also important here is that the correct answer to the question is only understood to be a correct answer if we approach this question as if it was maybe something like a question on a statistics homework problem set you're given, right? Let's think about this for a second. Let me come back to this previous screen. I hope you've had a stats class, and if you haven't, I'm sorry. But if you've had a stats class, you could imagine, easily I would assume, being given a question like this on a stats exam or homework problem where you are shown this exact question without the little blurb about his personality profile. And you're simply just told that I have a sample of people, 30 of them are engineers and 70 are lawyers. And I'm going to randomly select one of them named Jack, and I want you to tell me what's the likelihood he's an engineer. And you could say it's 3 out of 100, 3 out of 10, 30 out of 100, right? Or 0.3. Because that's a probability question, and you are given this question in the context of doing a statistics assignment. So you know that you're supposed to use the statistics information because that's what the class is about. That's what the homework assignment's about. That's what the question is about, right? And of course, in the course of taking the class, you are learning about probability theory. And you probably have questions, but it's different. You probably have something like, if I have a basket that has 100 balls in it and 30 of them are red and 70 are blue, and I'm going to pull one out, what's the probability of it being red? So again, you're going to give the statistical answer. But in this research, when you have a naive research participant come into the lab and they're presented with these questions, they don't know they're being given statistics homework, right? So they're not necessarily thinking in those terms. And on top of that, they've never necessarily had a statistics education. And again, we need to think about something else here, which is that personality profile that is provided to the participant. Why, when you're doing a stats homework, would a question like this kind of omit the personality profile? Because it's irrelevant to the question, right? If the question is really about the probability, then that personality information would be irrelevant. So, why would the researchers include the irrelevant information here unless they were attempting to get people to use this, right? In research methods, and if you've had a research methods course, you would have learned this term. And again, if you haven't, sorry, it's a demand characteristic, right? So what we need to do is we want to try to put ourselves into the position of the participants, the P's here, in this experiment. And let's say that I am a participant in this experiment. And let's say that I have a PhD in experimental psychology and have had graduate level statistics, which are all true. And so then I know all of the statistics, but I get into the experiment and I get that and I see the stats and I'm thinking, all right, that's relevant. But then I see this profile of Jack and I'm thinking to myself, why, why are they showing me this information? Is it because I'm supposed to use that in my judgment? So I'm supposed to take the statistical information and I'm supposed to combine that mentally with the profile information and estimate some new probability based on the combined input of both of these things. And maybe they just want to know how much weight I should give to the profile versus the base rate, right? And so I'm going to come up with a number. And maybe I'm going to decide to not go purely with the base rate, but I'm going to let that profile influence me a little bit because I think that's what the researchers are trying to do. And the nature of the experiment has just forced me to pay a little extra attention to that profile, even though it's technically irrelevant. Because I'm thinking to myself, if it's irrelevant, why would they even give it to me? So it must be relevant, and therefore it must be something I'm supposed to do, right? So that would suggest that what we're seeing here is not necessarily a totally accurate representation of real world decision making, so much as it is how people respond in a laboratory situation when they are presented with information and they're not exactly sure what they're supposed to do with it, but they assume they're supposed to do something, right? So that's the idea here, right? So as my note here is that people might misuse base rate data, right? But they might also fall for trick questions. So, and we know that's true, right? Here's some more biases here that also represent something that looks like statistics homework. So our new question is, the bias is called insensitivity to sample size, but here's our new scenario. A town is served by 2 hospitals. In the larger hospital, about 45 babies are born each day. And in the smaller hospital, about 15 babies are born each day. We're going to give base rate information, right? So as you know, 50% of babies are boys and 50% are girls, but the exact percentage is going to vary from day to day, right? So it's not going to be exactly 50-50 every single day, right? So some days higher, sometimes lower. For a period of 1 year, each hospital recorded the days on which more than 60% of the babies born were boys, right? So you can have a few outliers sometimes. It's, every now and then you're going to have a few days where you're going to have 60% boys to 40% girls or more, right? So which hospital recorded more of these days? Is it the large, the small, or is not really going to matter whether it's a large or small hospital? And that's what people will often pick, right? That basically if it's 50-50, it should be 50-50 for the large hospital and 50-50 for the small hospital. And if variations occur every now and then, come somewhat randomly, maybe you would expect the same frequency of variations to occur in both cases. But what probability theory tells us is that small samples are more likely to be prone to variance, and therefore small samples are less likely to be representative. And if representative means showing more 50-50 patterns, then small sample sizes are likely to deviate from our 50-50 patterns. So the correct answer is, in fact, B. But once again, people get it wrong. But as I have a little note on the bottom here, yes, in research studies in psychology labs, people get this question, quote unquote, wrong. But if you were learning about sample size and representativeness in a statistics class and you were given a question like this, would your answer change? And would you give the correct answer here, right? So does the context matter, right? If it's part of a stats test, are you going to choose B? Maybe. Depends on whether you were taught it. A couple more things here. The gambler's fallacy is another kind of probability mistake here, right? So this is the idea of believing that something is due to happen, right? So you're flipping coins. So the idea is that it's 50-50, heads and tails. But if you flip it four times and you get four heads in a row, you think to yourself, well, that means that maybe it's due for tails because the likelihood of having too many heads in a row is would be pretty low, and so I think it's due to switch at this point, so it can even these numbers out, right? But the idea here is that in these kinds of events, each event is independent of all previous events. So the probability of the fifth toss being heads or tails is still 50-50. It is not influenced by past events, and the coin has no memory in a sense, right? So this idea that the coin would be due to change its response cannot be true. But people think these things, right? They think about that kind of stuff. We might think that if there's a lottery, a weekly lottery drawing, and nobody has won it for many, many weeks in a row, that you think it's due for a winner. So you maybe you're tempted to go buy it. But again, that's no likely. The lottery has no memory, right? So it's not influenced by whether or not anybody won last week. Another example of a base rate mistake is the hot hand effect, right? So if you've heard of this before, if you're a sports fan, you might have heard people say that such and such person has a hot hand. This usually comes up in basketball because the idea that somebody has a good night shooting, right? So they're making baskets. They have a lot of streaks, and they make a lot of shots in a row. And you'll even hear announcers say this, right? Like you're at there's a game and it's got a close game. Um, and so now you got like maybe like 10 seconds left in the game, and you got the ball, you call a timeout, and you're going to call a play. So now the idea is that you want to make sure that your hot hand is the one who gets the ball and makes the shot and attempts the shot at the last second, right? Because you think that person is hot tonight. They are the ones with the hot hands, so they're the ones that are going to be more likely to make the shot, right? And so here, what the researchers did is they studied people, and they really established that yes, it's true that people do believe that certain players are very streaky, and that there are nights where they're hot and there are other nights where they're cold, right? Where they either make a lot of shots or they miss a lot of shots. But then what the researchers did is they went back and they looked at the actual shooting data, right? Game to game to game data, and they couldn't find any really significant deviations in their shooting percentage. And they also didn't find a lot of streaks. When they look at actual shot by shot performance within a game, they don't find a lot of long streaks of either consecutive misses or consecutive makes for those players versus other players who were not perceived as being streaky. And so then the idea that there are hot and cold streaks for certain players, and that means that someone is more or less likely to make their next shot, that doesn't really hold up statistically. So again, it suggests that we start to believe there are these statistical patterns when they're not really there. So that's a kind of a misjudgment of probability. Though it is fair to ask here when it comes to people making a prediction about the likelihood of something happening. So if I believe that such and such player is hot tonight and that they should be the one to take the game-winning attempt because I think they're more likely to make it, it's not as if this is a particularly random outcome, like flipping a coin, right? Flipping a coin is a random outcome, 50-50 every single time. But when it comes to making shots in basketball games or any other, outcome in sports performance, it's not a random outcome, right? It's a test of skill. And players can, in fact, be different in terms of their skill. So it might be the case that certain players maybe ought to be the ones who take the last shot because there are, in fact, real skill differences there. So anyway, that's our hot hand effect. Our last one here, the Monty Hall problem. So if you know the old TV show Let's Make a Deal, and there's two old ones. There was one from the 1960s and 70s, and maybe it persisted into the 80s. But there was another one on the air maybe 10 or so years ago, maybe 10 or 15 years ago. So the original host was called Monty Hall. And so here's how it works. People are called up on stage and they are shown three doors, right? So three stages, three doors with curtains or doors, and there's a prize behind them, right? So there could be a nice prize like a new car. And then the other two doors have some kind of thing you don't want, like donkeys and goats, right? So you basically have to pick one, right? So I want door number one, right? And so you don't know. You basically 1 in 3 chance of winning that new car, right? So you're gonna, or in my example, I say that the contestant picks door two. So then what happens here is that before we reveal the outcome to our contestant to see if they've won the car or if they've won a donkey, the host of the game show, Monty Hall, he's going to reveal one of the other two doors, right? But importantly, Monty Hall never reveals the car. If the person guessed wrong, there's a car behind door number three, Monty Hall's not going to open that and say, "Oh, you lost," right? So what he's going to do is he's going to always reveal the second goat or second donkey, right? So let's say that that's behind door number three. So he reveals one of the losers, right? Door number three. And so now you know that we've ruled out door number three as a winner at this point. So now you're asked, do you want to stick with your original choice of door two, or do you want to switch to door number one? So a lot of times people think they want to stay because they feel that their chance of winning is not necessarily any better, and they just hopefully they felt that they guessed right. But the statistics say otherwise. The statistics say that now that we have gained more information about which doors are not winners, that we should definitively switch our door choice every single time. That doesn't mean that we always win 100% of the time, but if we were to do this and play this game 100 times, we would win more often if we always switched our answer after Monty Hall reveals one of the losing boards, right? So again, though, people don't always kind of follow that and understand it, and sometimes even resist thinking that that's true. So again, does it suggest a misjudgment of probability? Yes, it does. Does it reveal something about human reasoning that we are not necessarily good with reasoning about probability? Yes, it does. Does it mean that we're bad at making decisions? Not necessarily, right? It just means that we might be bad in our stats classes and probability math classes. So, okay, a couple more biases here before we try to wrap up this particular video. Again, the availability bias also relates a little bit to probabilities. So here the argument is that if you ask people to think about things like what's the risk of dying in a plane crash, or what's the risk of if you go to the beach and you're going to get attacked by a shark, I hear a lot of people say that sometimes they're afraid of going to certain beaches and so forth. Well, I mean, sure, it can happen, right? It certainly has happened. But people are really sometimes overly dramatic about how much they fear these kinds of things and get anxious about those kinds of things, but they're not necessarily equally fearful and anxious about things that are, in fact, much more common: car crashes, over plane crashes, or getting cancer as opposed to getting a shark attack, right? So the things that are actually likely are things we don't worry about. The things that are really rare, people do worry about. So it again suggests maybe a distortion in how we think about probabilities and represent the actual likelihood of something happening. It's called the availability bias because these kinds of events, the shark attack and the plane crashes, are very dramatic, and sometimes they get featured on the news, and the footage and the stories are also really sensationalistic and dramatic. So they create strong impressions on us, and that makes them much more memorable and easy to think about. Whereas all of that other stuff about car crashes and people getting cancer, that's just the unfortunate but mundane reality of the world around us, that it happens daily, but it doesn't make the news. So it's just not that kind of a big dramatic sensationalized thing for us. Anchoring bias, this one not necessarily is a probability thing, but it just shows again how we use information and weight the importance of information is not always optimal. Um, so we got our choice here of subscribing to The Economist. We can choose a print subscription for $125 for a year. I can choose print plus digital for the same price, or I can choose digital for $59. There's a couple of things going on here, but one thing is you might notice right off the bat that the digital subscription is a whole lot lower. Um, so we might think that people are likely to choose that because what happens here is that that large price for the print or print plus digital is so large that it serves as something like an anchor. And in contrast to that anchor, the $59 seems like a deal. So I'm like, yeah, I'll choose that. And maybe I'll choose it even if I wasn't necessarily going to even subscribe to The Economist, but I'm thinking, hey, I'm getting a deal. And so if you've ever heard anyone do that kind of stuff, or like I bought something I didn't really need, but it was a good deal, maybe it's because, again, what they're doing is they're comparing the price that they paid for it versus the price that it would normally cost. And they're thinking, I saved a lot of money by doing this, even though they still had to spend money in the first place. And maybe it was money they didn't need to spend, right? But another outcome that could also happen is that you might choose the print plus digital because it's the exact same price as print, but it includes the digital of that would normally be $59. So you might think to yourself, I feel like I'm getting something for free here, right? And now you end up spending this much larger $125 because it feels like, again, you're getting a deal, but you're not necessarily getting the deal, right? Let's do, I think, just one more. I'm just going to peek at, okay, we're going to do 2 slides. All right, we'll do 2 slides. This one's pretty quick here. So on the recognition heuristic here, we're going to go with familiarity. So that relates to things like my example earlier about picking a restaurant to go to. A lot of times when we're faced with certain uncertainty and we can't, make a decision, we might just choose to take it easy on ourselves by going someplace we've been before rather than trying something new, right? So we're going to show a lot of kind of preferences for the familiar sorts of things. That can vary a little bit though, and that's where we might have to start getting into things like personality research because there are some people who have more of a preference for novelty, for example. So that means that maybe their preferences for familiarity is a little less. They like novelty, not familiarity. So these heuristics are rules of thumb for human behavior, I guess you could say. And then the Q heuristic, right? So what we're talking about here is, when I talked about coming up with an algorithm for choosing a college major, I listed a bunch of stuff, right? Like jobs and income and security and all these other things. And is that an exhaustive list? I don't know, right? Maybe there's more things to consider besides those things, but I don't necessarily know every single thing that I might need to think about when it comes to making a decision about whether to major in one thing versus another. So I'm just going to come up with whatever list I can think of, and I'm going to just list those values, and these become like the pros and cons, right? That doesn't necessarily mean I've really comprehensively analyzed everything I need to. I've really only thought about the things that came to mind. And so that's what we call a cue heuristic here, is I'm just going with certain cues that are easy to think about, and that's going to influence me. It's not comprehensive, it's not exhaustive. So again, it's a heuristic. It can lead to mistakes, but so can algorithms. Okay, let's wrap it up here. So yes, judgment under uncertainty is full of biases. Yes, it is true. People are not good at statistics and probability. And if you've ever taken that class and you got anything less than an A plus, you know this to be true. We don't use probabilistic information in an optimal way. We are not rational in that optimal way. We do use heuristics. And it is easier to do that, right? It is much easier on our limited cognitive abilities with limited resources and limited working memory capacity. This is called satisficing, right? So as an alternative to optimizing, where I have to be a computer and I have to think about and do this kind of optimal mathematical judgment, I will just satisfice. I will take the easier approach because the easier approach might be somewhat less optimal, but it is not necessarily a whole lot less optimal, but it is a whole lot easier to do, right? That's the take-home lesson here. And I guess we can wrap it up right there. So we will have, of course, another part two for this chapter. And until then, always let me know if you have questions.